Whoops, I apologize for the technical issues there. I'm not quite sure what happened, but the video cut off. But anyway, just to kind of summarize where we were at, we were trying to minimize this function, p equals 200 over y plus 2y. We were working on the interval 0 to positive infinity. We had figured out that we only had one critical number right here, y equals positive 10. And we had said, okay, if this is a maximum, it's not just a local maximum, it's actually an absolute maximum. And if it's a minimum, it's not just a local minimum, it's an absolute minimum. I just need to figure out, well, is it a maximum or a minimum? I want a minimum. So it's up to you how you want to figure that out. You can use either the first or the second derivative test. It's completely up to you. I think I like the second derivative test better. I think it's just a little bit more straightforward. You may be more comfortable with the first derivative test, and if you prefer to use it, then that's totally fine. I'm going to rewrite my first derivative over here. We said that was negative 200y to the minus 2 plus 2. My second derivative, p double prime, is equal to let's see, positive 400y to the minus 3, derivative of 2, that's just 0. So this is 400 over y cubed. So I'm going to take my one single critical point, which is 10, and plug that into my second derivative. P double prime of 10 is equal to 400 divided by 10 to the third. So this is really 400 divided by 1,000, which I don't really care so much about. I could figure it's 4 out of 10, what is that, 0.2 as a decimal. Really, I care about the sign of that number, right? Because we're looking at the second derivative, I care about what is the sign of this. Well, it's a positive 400 over 1,000. So the second derivative is positive. What does that mean? Second derivative is positive. This means that my function is concave upward. And that means that, yes, I have a minimum. That's exactly what I wanted. If I had a maximum, I'd be in big trouble. I'd probably need to go back and check my earlier work, check maybe my first derivative or my second derivative, check my critical point, because I should end up with a minimum here. If I don't end up with a minimum here, can't finish the problem. I don't know what to do in that case. So we have our minimum. We say y equals 10. So one of the dimensions is y equals 10. The other dimension, remember, we can always go back to our constraint. So we can always go back to 100 over y is equal to x to solve for the other dimension. So we're going to take 10, plug that in for y. So x equals 100 divided by y. Oops, we said y was 10. X is also 10. So if my area is 100, and if I want to minimize the perimeter, I need a rectangle with 10 units by 10 units. Well, shoot, that's just a square. So if I want to minimize my perimeter with a given area, I just want the square that has that area. So that's it. If I want to minimize perimeter in this case, the answer is a square. A square will always have the minimum perimeter of all rectangles that have the same area.